Well, right then. So, well, first of all, well, I'm Ender, for those who don't know me. Short for Intel OTC, and I've been working with Christian and the Wayland team doing Wayland stuff. So if you saw the program at first, it said something about a sonic page flip, but we changed the program. So instead of me giving a 1 hour talk, we divided this into 1/2 hour talk. So the second half of an hour, Vile is going to talk about the kernel stuff, the kernel part of the sonic page flip and whatnot. So, well, the idea of this talk is to talk about a little bit how we use overlays and the plain, well, not only the hardware overlays, but about the architecture inside Weston, that how we organize surfaces and how we use the overlays and other things that I'll talk about later. But it's more about the architecture inside Weston than the hardware overlays. But before I go into that, I just wanted to, talk a little bit, very brief overview of what Weston looks like in terms of architecture. Well, I guess I should have mentioned that Weston is the Wayland's reference compositor, as someone know that. So we basically have this division. There's the shell module that doesn't really matter for the purpose of this talk. Then you have the main compositor, and that's basically what handles your surfaces, surfaces being the equivalent of windows and things that have image on the screen. And well, we have a backend that is the part that actually knows how to talk the hardware, and well, not necessarily just the hardware, but we have a X11 backend, we have a nested Wayland backend, and we also have this split with the renderer, because the compositing part, up until very recently, could only be done with OpenGL, but now we have this renderer API, and we can actually split all the compositing part of it, and we actually have a Bixman renderer today, so we have this kind of flexibility. Although the backend needs to be able to interact with the renderer, so that's why you see that weird dependency over there. So before you go into the actual overlays, I just want to talk very briefly about the repaint cycle inside Weston, how it composites things. So when I talk about the overlays, it makes sense. It makes a little bit more sense of what's different when you're actually using overlays. Basically, the repaint is it's a very simple thing. You have a stack of surfaces and you draw it backwards. So basically, suppose you have this typical Wayland scene, spinning triangle and whatnot. You have all the surfaces a background, and the drawing is like the super simple thing you would do to draw backwards. Except that we have this, by the way, if you see the cursor over there, in Wayland we have the cursor is not something special. It's for the purpose of the backend and everything is just a regular surface. It's like a window, and the clients provide the content for the cursor as they provide the content for a surface or any surface. So, well, this might become clearer later. But besides, the only optimization, well, maybe not the only, but we have this optimization where the clients might be using an ARGB visual, and they might have opaque content. So we allow the clients to say, well, I have this ARGB surface, but look, this part of my surface is actually opaque, so you don't need to use the alpha channel. And so that allows us to disable blending when we're compositing the opaque area, and it will also allow us to use overlays in some cases, you can see later. So basically, before the repaint cycle starts, we iterate the surfaces, looking what are the regions that we need to clip, so that we don't redraw things that are necessary. So for instance, when we're looking at the surface, we're accumulating this green region that is the opaque region. And so, for instance, when we look at the hypnotic pattern there, what we see is that we can actually clip those regions and only draw that. So having said that, so this is how we actually do the compositing inside. Well, when we have the normal operation, when we don't have any planes, any overlays, we just have this compositing that goes like that. But the idea here is that we have this logical plane inside Weston that is it's basically a group of surfaces, and the idea is that well, in some level, what we do is we basically have well, we can split the surfaces in different groups, and the idea is that we have a plane that we call primary. It's basically everything that is in primary plane it goes through the renderer. The renderer will actually use the contents of those surfaces and composite the contents of the primary plane. But we want to give the backends a chance to use harder overlays. So before we start repainting, we tell the composite, the backend, hey, you can assign planes now, and it has a chance to see how it can shuffle around the surfaces into different groups of planes, so that we end up rendering less and taking advantage of the overlays. To exemplify that, I think it's easier to talk about the things we can support with the DRM backend. Well, you see that we have the cursor plane, so we have the support for hardware cursor, and it is kind of an overlay. It's a special overlay, but you can see it just as an overlay. We have this scan-out plane is actually something that is not really a hardware feature, but the architecture actually lets us composite less just by using this scan-out plane. It's basically a software optimization, but it ends up being a plane in this logical sense. And we have the sprite planes are actually the use of hardware overlays. So if you look at the planes stacked, what you see is if you had surfaces stacked in all those planes, you have a primary plane where basically probably most of your surfaces would be. Then, well, the scan-out plane, and the idea is that one thing is on top of the other. So if you're using the cursor plane, anything that is in the cursor plane would be on top of everything else, and so on. So let's start with that scan-out plane that is the software optimization I said. The idea here is basically when you have a full screen application, you know that it covers your full screen, so you don't really need to render anything that is beneath it. So the idea for a very simple example is, suppose you have a game, and this is full screen and covering that other part of the screen. So you might still have your triangle spinning in the back or something going on there, but you don't really want to render anything beneath it. So at that point, what we can do is, what we do is, we check, well, this surface actually fits in this plane. It has the requirements for a scan-out plane is basically the buffer, the buffer that backs this surface. It is the size of the screen, and it's a buffer we can scan out from. So at this moment, what we do is we stop rendering, and we simply stop rendering. So if we get to that plane, at that point, instead of calling into the renderer and asking it to composite the contents of the surfaces, instead, what we do is we program the display hardware to scan out from the buffer that was rendered by the client. So that means that we have zero compositing. And the overhead is only that, well, we still need to go through the compositor to ask for a page flip, and then the compositor will get the buffer, do the DRM part of it, create the FB and whatnot until you program the hardware to scan out from the buffer. But it's a very low overhead, and you disable compositing. It's like disabling compositing when you go full screen in Next, I guess. So I guess that's the basic idea. So drawing is actually wrong, that when we actually using this, you end up having nothing on the primary plane. It's not just data. But my idea here was just to show you that what ended up in each plane. But in that case, you wouldn't actually have anything there. So the sprite planes are actually B planes that use the hardware overlays. Here we need to use and that's the part where we actually need the atomic page flip, because what the atomic page flip let us do is at the same time as we flip the CRDC, the back buffer with CRDC, we can flip the overlay and make sure that the image is consistent, but you get to see more of this on VIDA stuff. So suppose you want to see a really oversized bunny in a movie. You might be watching your movie, and in the case where it's not full screen, or say the buffer is actually, it has a different color format, so you might be interested in using the hardware overlay to display it. In that case, we can actually program the hardware in a way that what you get is we stop rendering that white area in the middle of the primary plane and just program the display hardware to do the overlay and let that part of the display hardware do this and not have the renderer do anything. Well, it will still need you to draw the surroundings of the buffer, but through that opaque optimization, we actually stop compositing all that part of the sprite plane, the primary plane, sorry. So the other plane we have on the DRM backend is the cursor plane. And I said it was a special overlay because you have very tight restrictions. You can only support certain sizes of cursors. Right now that's 64 by 64 for us, but I don't know if there's hardware that supports bigger cursors, but who needs a bigger arrow? But this is a tricky one, because basically you have the restriction that the buffer for the cursor, it actually needs to be 64 by 64, and the stride needs to match the width. So, for instance, for the path where Wayland clients allocate buffers, they don't really have a way for the clients to allocate that buffer. So we can't really have the compositor just take that buffer and program the cursor overlay with that. So what we actually do is something different. Maybe I should have mentioned earlier that we have clients, in Wayland we have clients that can, accelerated clients that render GL and then they render to a buffer that is in video memory, or they can also be shared memory, and then we use the shared memory as a text stream. We upload that data from the SAJ buffer to video memory. So in that case, for the cursor planes, we only support the cursors when using SAGM data. And what we do is when we initialize the backend, we create these buffers that fits the cursor. And at the moment that we see a change, say, well, the surface that was using the cursor plane, the content of it changed, and we re-upload, we copy the content from the shared memory to the buffer. So, I mean, since cursors are something that are not really animated, and this is a tiny copy anyway, it's not really a big overhead. And it's really important that we have the cursor support, because say if we had to composite the cursor over an overlay, maybe an image later here. But well, I get back to that. So this is pretty much what happens when you have the cursor plane. You have your cursor plane in a separate plane and not in the buffer that the CRTC cans out from. So basically, the plane assignment, I said that before we start repainting, the compositor the backend has a chance to shuffle surfaces around, so it decides what surfaces end up in using an overlay. So right now we have a very simple implementation that is, we just iterate the surface list from top to bottom and see, well, do the first, for instance, we're seeing this surface that is the cursor surface. Can we put that surface in some plane? And then we're going to see, well, this is a SHM buffer. This is less than 64 by 64, so yeah, okay, we can do that. So, okay, move that to the cursor plane. Then we end up here, see, well, we have this surface, it has a YU, YV buffer format. We have a YU, YV overlay that supports it. And there might be scaling involved, so we need to check if the scaling is right. But say, well, okay, this surface we can actually put an overlay. So we move it out of the primary plane. And then we go to this surface, but this is the panel is not opaque. It has an alpha channel, and so we need to do alpha blending, and we don't have any overlay that can do ARGB. So basically in that case, we can't do anything, and if we continue the process, basically, that's what's happened. There's also one thing that we don't support is, suppose we had an actual overlay that would support that surface that is beneath the terminal. But right now we don't support using an overlay that has overlap. So that wouldn't be useful either. But in that case, what happens is we end up with the cursor in the cursor plane, well, that in the overlay plane. And in the end, you have this 3 different buffers, and only when the video signal is being generated, this image will be composited. So basically, the idea here is that we automatically put the surfaces in overlay. So the clients didn't have to do anything except maybe set their opaque region, so we can actually know that we can put them on overlay. But we let the compositor decide who goes to what is the surface that ends up in an overlay and whatnot. But as I said, their implementation is really simple. So suppose we had this scenario where we have we have those two surfaces, the triangle and the video, but the triangle is on top of the video on the stack. So given our algorithm, we end up seeing that the triangle can fit in the overlay, and it can fit in the overlay. So we would assign it to the overlay and have the overlay already taken. And then we start looking at the video to see, well, it could go to an overlay, but we don't have any free overlay that we can use. But obviously that would be a bigger win, because the video, well, it covers a bigger portion of the screen. So we end up compositing a lot less with that surface in overlay. But that's an area for improvement. But another way, let's say we would have to balance it for the given workload. So I guess that right now we're not really sure what the workload we want to optimize for is. So we're not trying to do any premature optimization. But we could improve even to have those kind of scenarios covered. And well, that's pretty much it I wanted to say about the part of assigning the planes. And now I wanted to run Weston here and show you, try to give you an idea of how does this work automatically frame by frame. So what I'm going to do here is enable this debug feature, where basically what this did is it recompiled the shaders so that everything that's used in OpenGL is being composited looks kind of greenish. So suppose I have my spinning triangle here, and you see that, well, it's beneath the panel, so we're doing alpha blending here. But when we move it out of the panel, so it stops doing alpha blending, then you see that it automatically moves to an overlay. So this is not greenish anymore because it's using an overlay. And also what we have here, you see that the cursor is actually not, the cursor is also actually not greenish because we're using the harder cursor. And one thing is, we don't really need to use it, like, it's not only the cursor that can use the cursor overlay. For instance, I hacked simple SAGM to be smaller, so it would fit on the, you see this tiny window here.
And are you using the atomic mode setting from page flipping stuff for this?
Yeah.
Do you see any cases where you get a visual difference between the sprite version and the composited version, the geocomposited version?
I haven't really seen anything
Like
like
color calibration differences or anything?
that.
I guess with this you can't tell because it turns green.
Yeah. Yeah. I mean, I didn't try any really sophisticated, let's say. I've been trying this mostly with spinning triangles and that kind of thing. So I guess it was a bit. I didn't notice anything, but well, I guess with the projector it won't be easy to notice anything either. But what I wanted to show here is, for instance, look at the simple SAGM, and the moment we hide the cursor, it actually went to the cursor plane. And this is a bug because basically the cursor overlay has alpha, but the simple SAGM client, it says it's opaque, but it paints a hole in the alpha channel, so you actually can't see, can debug this kind of things. But when I do in the demo, I didn't manage to fix that. But the idea I wanted to show here is that we can actually use the cursor overlay here. I'm using the cursor, there's a cursor here on my laptop screen, and then we are using the harder overlay cursor there to show something else. And I also have an example. I hope it won't crash because I had to do some changes here, but well, I didn't show the scan out plane, but when it go full screen here, it's still not greenish because we're actually scanning out the buffer that the spinning triangle client rendered. So there's no compositing going on. But we can even get to the point where have this other client. And if I go full screen and add this menu here, oops, down, needs to work. Crap. Okay, this was supposed to go to, the menu was supposed to go to an overlay, and we would get the scan out plane, the buffer, the scan out plane, the menu and the overlay, and then we have the harder cursor, and we would have this without any.
I think the menu is transparent.
Well, I made it opaque
Oh, it has
for the demo. Sorry?
It has rounded corners.
Yeah, well, it was just for the demo, but
Oh.
it has round corners, but well, since that doesn't work, I guess I can stop here and take questions. Okay, no questions.
We're doing the finish thing. We're all very silent. And then,
Okay. Well, there's 7 minutes. We can just be silent here for 7 minutes. Or maybe Peter wants to get started.